Welcome back to Differential Equations. In this lecture, we're going to learn how to solve a second order ODE with constant coefficients. All right, so let's think back to our previous lecture. We introduced a second order linear ODE of this form, and we pointed out a few ways for it to be linear. Y and its derivatives were raised to first powers, and the quantities multiplying y and its derivatives are just functions of x. So here we refer to the functions a2, a1, and a sub 0 as the coefficient functions. When we introduced this differential equation, we did so by already being given one solution, and then we asked the question, with one solution, how do we find the second solution? Because we expect from our previous lecture, a second order linear ODE should have two linearly independent solutions. Now, we know how to do that given one solution, finding a second solution. The question that we're going to address now is, how do we even find one solution to begin with? As it turns out, it is extremely fast for us to find both solutions, provided the coefficients are now constants. So for this lecture, and for the next few, we're going to focus on second order linear ODEs with constant coefficients. So here, the coefficients A, B, and C are just numbers. They're not functions of x. We'll come back to that a little bit later in a few lectures. All right, so this is the general type of differential equation that we'll be focusing on in this lecture, and basically the two that follow. Now, these are going to fall into two categories. The first is called a homogeneous differential equation. And be careful, we're using the word homogeneous differently in the context of a second order ODE compared to how we used it in the context of a first order ODE. So for us now, homogeneous just simply means the right-hand side equals 0. So the right-hand side, what we've been calling g of x, that is just 0. All right, the second type is non-homogeneous, where the right-hand side is some function of x, non-zero. All right. So for this lecture, we're just going to focus on the first type, a homogeneous second order linear ODE with constant coefficients. All right, so when you're ready, let's get into how we're going to do this. But first, we should probably review some examples that we've covered in previous lectures. So let's take a look at this one here. This was introduced in a previous lecture. It is second order. It's linear, and the coefficients are constants. All right, and we propose this example, given one solution, y1 as e to the x. We went through the procedure reduction of order to find the second solution, e to the negative x. All right, and there was some work involved in that, but given one solution, we could find the second solution. All right, here's another example from that. So we were given one solution, y1 as e to the 2x, and again, we ran through our reduction of order procedure to find a second linearly independent solution, y2, which we found to be e to the 3x. All right, now with these two examples, you might start to get the feeling that all solutions are exponential functions. And as it turns out, they are. So every single second order linear ODE with constant coefficients has solutions that are exponential functions. We're going to write them in the form, in this important remark here, as y equals e to the rx, and our goal is to figure out what the values of r are. All right, now the previous two examples there seem to fit this statement, right? y1 and y2 in both examples are exponential functions. Well, let's go back to arguably the most important second order ODE that we've been mentioning from our very first lecture, y double prime plus y equals 0. All right, now at the time when we introduced it, we just rewrote this, subtracted the y term to the right-hand side, and we saw pretty easily that sine and cosine are solutions. All right, sine and cosine, those are trig functions. And there seems to be an immediate contradiction. Sine and cosine are not exponential functions, as that important remark right above is claiming to state. So how in the world are we going to resolve this? We see clearly that sine and cosine are solutions to this differential equation, but yet there's this remark or theorem saying all solutions should be exponential functions. Well, this is probably the first time many of you will be brought to arguably the most important equation in mathematics and physics for that matter. And we're going to pick up with that, with kind of this question. We see that sine and cosine trig functions are solutions, but the theorem is saying exponential functions are solutions. So the question, which we will answer, is there a relationship between exponential functions and trig functions? And what I'm hinting at is that the answer is yes, there is a relationship. There's a formula that we'll mention, but we're going to save that for later in this lecture. So we'll come back to reconciling this once we proceed with some basic theory. All right, now let's use that kind of important remark, that theorem, to guide us through this. All right, we have a second order linear ODE that is homogeneous. The right-hand side is 0 with constant coefficients. All right, the remark, the theorem, basically said that all solutions are of the form y equals e to the rx, where r can be any type of number. All right, now what we expect is we should find two linearly independent solutions. Now we're going to kind of work backwards. We're going to basically plug in this solution, y equals e to the rx, and then figure out what are the values of r that make it a solution. All right, in order to plug y equals e to the rx into the differential equation, we need to calculate the various derivatives. And that should be a piece of cake with the chain rule. So each time you differentiate e to the rx, you get a factor of r. So y prime would be r e to the rx, and y double prime would be r squared e to the rx. All right, now if we want this to be a solution, that means that it should satisfy the differential equation. So we're going to plug it back in, make a replacement for y, y prime, and y double prime, and we get this equation. Now this we can simplify. Notice each term contains e to the rx, so we can factor that out. And what we get, the part within parentheses, that's what we're interested in. We're trying to find the values of r that make e to the rx a solution. So we can just divide the exponential off here, and we get this, which we call the characteristic equation. So for our differential equation above, the one with constant coefficients, this is referred to as that differential equation's characteristic equation. And it is deceptively simple. We're trying to solve for r. This is merely a quadratic equation for r. And think, quadratic equations at this point in your your coursework, those are extremely simple to solve. Ideally, they factor. If they don't factor, you can solve for r using the quadratic formula. So at most, solving one of these differential equations, solving this characteristic equation, should take you maybe 30 seconds maximum. just using the quadratic formula to solve for R. All right, when you're ready, let's get to some examples to see how this works. All right, before we do that, let's just give an overview since there was a lot of terms. So our first step, we assume a solution of the form y equals e to the rx. We plug y back into the differential equation, calculating the first and second derivatives. And what we arrive at and what we solve for R is this equation called the characteristic equation. All right, now because this is a quadratic equation, we expect there to be at most two solutions. So from that, each value of R corresponds to an exponential function that is a solution, e to the rx, for the different values of R that you find. All right, and each of those values of R gives you one of those linearly independent solutions. We expect there to be two linearly independent solutions since the differential equation is of second order. And with our linearly independent solutions, what we've been calling y1 and y2, we get the general solution, which is a linear combination of y1 and y2. So we would write our final solution here as y equals c1 times y1 plus c2 times y2. Here, c1 and c2, those are our integration constants. If we have initial conditions, we can solve for the values of c1 and c2. All right, now before we get to our examples, definitely maybe have this copied into your notes, pause if needed, and when you're ready, let's get to some examples. All right, now I'd like you to make an attempt at this one. Even though we briefly mentioned it, solving the characteristic equation is as simple as solving a quadratic equation. Now, if you've been feeling comfortable with the content of this lecture so far, this probably takes you at most a minute to solve. Pause, make an attempt, and we'll check in about a minute. All right, welcome back. So we're going to go through those steps as we outlined a few minutes ago. So first step, assume a solution for y of the form e to the rx. Calculate your derivatives with the chain rule. Plug all those quantities into the differential equation. Factor out e to the rx, and you get the characteristic equation. Here, that is r squared plus 4r plus 3 equals 0. All right, now always try to factor, and here it does, factors very quickly as r plus 1 times r plus 3. Set each of those factors to 0, and we get two solutions for r equals -1 and r equals -3. These values of r, we refer to them as the characteristic roots. So we got two values as we expect for a quadratic equation. Each value of r gives you an exponential function as a solution. So we might say our y1 is e to the -x. That's using r as -1. And then y2 is e to the -3x, using r as -3. All right, and we just put them together as a linear combination of y1 and y2, giving us the solution to our differential equation here. And with the initial conditions given at the top, we can actually solve for C1 and C2. All right, now this is kind of the first part. We have our solution or general solution, and we can now use the initial conditions to solve for C1 and C2. All right. When you plug in the function initial condition, y of 0 equals 7, replace all x's with 0, so you get exponentials e to the 0, which is 1, and you get this equation, 7 equals c1 plus c2. By itself, that cannot be solved for c1 or c2. That is two unknowns. We need a second equation, and that's where the derivative initial condition comes in. Just be careful to make sure you correctly calculate the derivative of your solution, y, with the chain rule. There's going to be some examples later in this lecture where you might have to calculate the derivative of y using a combination of product and chain rules. All right, so I have off to the side there, the right in red, the derivative after using the chain rule. And now if you plug in the information for your derivative initial condition, you get a second equation, negative 17 equals negative c1 minus 3 c2. Now we're in business. We have two equations for the two unknowns, c1 and c2. And you can solve this very quickly with elimination. Notice if you add those two equations, the c1 terms subtract out or cancel. And you can very quickly find that c2 will equal 5, and then plug that back into the first equation to find that c1 is 2. All right, at this point, we're done. Just replace c1 with 2 and c2 with 5, and you get your solution with the initial conditions being satisfied. All right, hopefully that wasn't too bad. Notice the characteristic equation here, very easily factored. Let's take a look at another example when you're ready. All right, now you might feel more confident with attempting this one. So I would say pause and give yourself a few minutes for this to attempt it. You should expect to find two linearly independent solutions. So pause, give yourself several minutes, make an attempt, we'll check in after that. Welcome back. Now you should, or I would say you ideally found one solution rather quickly. So let's go through that. Again, assume y equals e to the rx, calculate your derivatives, plug it into the differential equation, factor out e to the rx, and we arrive at our characteristic equation, r squared minus 4r plus 4 equals 0. All right, now this one actually does factor. You can factor it as r minus 2 times r minus 2, which we can write that as r minus 2 squared. And since the same factor occurs twice, we get what's called a repeated root. So the solution for r is just the value r equals 2, but since there's two factors that are the same, we call that a repeated root or a repeated solution. Now that value of r gives us one solution, y1, which is e to the 2x. However, we do expect there to be a second linearly independent solution, y2. How do we find that? Man, it'd be nice if we had a procedure to go from having one solution to finding a second. Reduction of order. That's why we introduced that a lecture or two ago, so that way we can use that now. So in the case that we have a repeated root to the characteristic equation, there's a very simple form for the second solution. But let's go through the work on how we would find y2 here. All right, and I'm going to put up all the work here on the screen. Definitely pause that and make sure you thoroughly understand that. But this is merely the procedure that we outlined, again, in a previous lecture, how when given one solution, we can find a second solution. All right, and if you go through that, your second solution, y2, is always of the form u of x times y1. At the end of this example, you would find u of x is just x. All right, now with that, that gives us our second solution, y2, as x times e to the 2x. The function u that we would have solved for, u comes out to be just x. All right, and at this point, we are done. y1 is e to the 2x, y2 is x times e to the 2x. And we get our solution. There's no initial conditions here, so this is as best as we can leave it. We don't have any information to solve for the values of C1 and C2. All right, now I want to use this example to kind of summarize what happens in the case always when you have a repeated root. And this is one of those things where I'd like you to work it out once, as we did in this example, example 2 here. And we'll just summarize. If the characteristic equation has a repeated root, then the second solution beyond y1 as e to the rx, the second solution, y2, is x times e to the rx. And that always remains the same. So when you have a repeated root r, y1 is e to the rx, y2 is always x times e to the rx. And I would advocate to never go through the reduction of order procedure again. Just memorize that in the case of a repeated root, y2 is x times e to the rx. Otherwise, you end up spending, just think how long it takes you to go through the reduction of order problems, 4, 5, maybe 10 minutes, just to be careful and check your work. So just use here y2 as x times e to the rx. Much quicker. All right. So hopefully you're feeling pretty comfortable with this content so far. Basically, a differential equation now with constant coefficients. Just comes down to solving a quadratic equation for r. All right, so how could it get any more complicated? Or how could this be a little more complex? Let's see. Let's go back to our motivating standard second order ODE, y double prime plus y equals 0. And we do know that y1 equals sine of x and y2 equals cosine of x. They are solutions to this differential equation. Well, let's see what we get by using the characteristic equation. So we're going to ask, for this differential equation, what are the characteristic roots? All right, seems very straightforward. Assume a solution of the form y equals e to the rx. Calculate your derivatives, plug into the differential equation, factor out e to the rx, and we get this characteristic equation, r squared plus 1 equals 0. Now, you can use the quadratic formula for this, but it's just much quicker to isolate the square term and then cancel it by taking a square root. However, what we're led to are imaginary values for the characteristic roots. You do get two values here for r, but they are plus or minus I, where I is the square root of -1. Now, what does that mean? Well, each value of r gives you an exponential function that's a solution. r1 is positive I, r2 is negative I. So we get our solutions here, y1 as e to the ix and y2 as e to the negative ix. Those are definitely not trig functions. Well, what this is pointing to, again, what we hinted at the beginning of this lecture, is there must be some sort of mathematical relationship between the trig functions sine and cosine and these exponential functions, which we'll call complex exponentials, e to the ix and e to the negative ix. Now, what is that mathematical relationship? Well, we're going to get to that in part 2.